Hi, today we're reviewing our parent functions that we learned from Algebra 2 Advanced. In Algebra 2 Advanced, you studied 14 parent functions, so we're going to quickly just recap them so you remember. If you are coming to us in Pre-Cal Advanced from an on-level Algebra 2 class, you probably didn't study all of these functions, so you may want to do a little bit of prep work here and make sure you're good and comfortable with them. Okay, then we're going to add the last two new parent functions that we're going to study this year in Pre-Cal, just so you kind of have them all in one place. So in Algebra 2, you studied constant functions, linear functions, absolute value, quadratic, square root, cubic, cube root, rational odd, rational even, exponential decreasing, exponential increasing. You looked at exponential increasing base e. You looked at common log, which is logarithms in base 10. You looked at natural log, which is logarithms in base e. And then we're adding the greatest integer function, and really there's not a cool name for the last one. It's just absolute value of x over x, or you could turn that upside down and say x over absolute value of x. You see it both ways in calculus. All right, so the first one, constant, f of x equals c, and c could be any number. So f of x equals 3, f of x equals 2, any number. We're going to pick 4 for the purpose of our example here. So what that means is we have a horizontal line across the graph at the y value of positive 4. So if you look at the table, you can see that even though you're changing your x values, -2, -1, 0, 1, 2, all of the y values are the same, and that's a constant function. We have the linear function, f of x equals x. So that is a line that goes to the origin, has a slope of 1, and it is a positive slope because it's rising as you move to the right on the graph. So as you can see in the table, we would go -2, -2, -1, -1, 0, 0, 1, 1, 2, 2, and that's what generates this linear function. Remember, the linear functions never bend, so it's always going to continue in that pattern. And then we have absolute value function, which is actually a piecewise defined function. It's actually two lines that meet at 0. One on the right side of the y-axis has a positive slope, but on the left side of the y-axis it has a negative slope. And so you can actually define it in the piecewise definition there to your left, where you can see f of x equals, and that big little squiggly bracket, and then you have x from x greater than or equal to 0, and then you have the negative x's when the x's are less than 0. And notice that 0 is only included on the top one, not the bottom one, because if you included it in both places, then you would have 2 points at the same location, which would fail your vertical line test. But we studied the function equation of this more so than the piecewise function of it, and that's the bar x bar equation at the top. Quadratic functions, f of x equals x squared. Like the absolute value function before, it does have an origin point. So you're seeing that it's increasing on the right-hand side, but it's decreasing on the left-hand side. It doesn't go below the x-axis. It does include the point at the vertex, just like the absolute value did. Except in quadratic, it's a curved graph, where in absolute value, it's a linear positive slope on the right side and a linear negative slope on the left side. So you actually have two different pieces of an equation to make the graph. Here we have one piece that's continuous all the way around. And that's a pattern you should have learned really well in Algebra 2. So we know if we start at 0, then we go to the right 1, up 1, to the right 2, up 4, because you would square each of those numbers, right? -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So those are the basic numbers that all hover right around the origin on the left side, the right side, and at 0. We have the square root function, f of x equals the square root of x. It is a radical function. All of them are radical, so we could have cube root, fourth root, square root. And so in this case, it starts at the origin, and then it continues curving to the right, but it doesn't go back past the origin. So it has an endpoint at the origin. So it does have a value at the origin. We would include that if we were trying to put it into domain and range. And then it's going to grow there to the right. You can see at your table, the endpoint is 0, 0. That is extremely important. If you're listing points in a square root graph, you have to have the endpoint included as part of your table, because that is a definite interesting point on the graph that we need to make note of. Thing about graphing square root graphs, if you remember from Algebra 2, is sometimes they grow so fast that you may only have the end point and one other point on the graph. Where usually we'll have like 3 points on a graph. But this is one of those rare instances where you have to know the shape because you may only have 2 points there to use. So that's our fifth graph. Now we have cubic function, which is x to the power of 3. That's like a polynomial function. The base is the variable, the exponent is a set value, and it's a wiggle graph. So it starts low, it goes to the origin, and it comes up. There is that point of inflection at the origin, and notice it goes on the left side, it's increasing, and on the right side, it's increasing, but at the origin, it's just 0. So you can see in that table, we have our -2, -1, 0, 1, 2, and when you cube each one, -2 times -2 times -2 is -8, -1 times -1 times -1 is -1, and same thing is true for the other parts of that graph. So just like a line, its domain is all real numbers, so you go from negative infinity to positive infinity. You wouldn't have to worry about any bottoms to the graph like you have to worry about when you're doing range for absolute value or quadratic. This is just all values work both directions. So then we have cube root function, which is another radical function. And so notice in the cube root, you have a little 3 in the little check mark part of the graph. Anything above 2 will have a number there to tell you what it's talking about. And so what this is saying is what times itself 3 times would give you a value that comes out of the symbol. So you can see it wiggles, and some people will look at this and see right there at the y-axis, they go, oh, well, it's vertical right there, so it fails the vertical line test. But it's not, it's just increasing at a different rate from the rest of the graph. So this is a function. It doesn't fail the vertical line test at all. You can see from the points around the origin, -8, what times itself 3 times gives me -8. And that's what the y value is, which is -2. What times itself 3 times gives me -1? Well, the y value is -1. And so that's what that radical function means. Anytime you see the little check mark kind of things, and then you look in the index, which is that little number. 2 has no index. We just know it's square root, so that's a 2. Everything else will have a number there. So then we have graph 8. So now we're moving into the rational functions. Rational functions are fractional functions. And rational odd is f of x equals 1 over x. And so it's not a line, right? Because that x is on the bottom. So even if we look at it and we move that x up and say x to the -1, it's still not just an x. So the reciprocal function is what this is. Reciprocal of a line is a rational odd function. And the rational odd function has a branch in quadrant 1 and a branch in quadrant 3. But it also has a vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. So remember back from your study of functions in Algebra 2 that you can sometimes cross a horizontal asymptote, but you can never cross the vertical asymptote. So that's what causes the graph to break and have 2 branches. We know that we can't divide by 0, so when the denominator of the fraction approaches 0, it just kind of says, uh-oh, can't do that, and it causes the graph to split. And so it's splitting every time the denominator could be approaching or be trying to become 0 because we know we can't divide by 0. Now that's not to say we couldn't have something like x plus 3 on bottom and it'd be okay at somewhere else, but just the fact that it's just an x in the bottom of this equation makes it rational odd, and it makes it break on the y-axis where x would be 0. All right, graph 9, rational even function, also known as a reciprocal function. And this time it's f of x equals 1 over x squared. And I always kind of talk to my Algebra 2 folks about this, and it kind of looks like a volcano, right? It's going up and exploding up in the top. So in a rational even function, you have a branch in the first quadrant, just like you did rational odd, but you also have a branch in the second quadrant this time, not the third. It's as if, since everything is going to give you a positive y value, there's no number that you can square that will ever give you a negative value. You can see there's no negative y answers. So it's almost like we've taken the graph that was in quadrant 1 and quadrant 3, and because we're squaring it, we just flipped it up into the second quadrant where all of my y values will remain positive. And it does have a vertical asymptote because as x squared is 0, that is impossible, so it causes the graph to break vertically at x equals 0. and it has a horizontal asymptote on the x-axis. So that graph never goes below that, and in this case, it doesn't cross the horizontal asymptote. You learned in Algebra 2 that you could check to see if it was going to cross it or not, that we know from our parent function knowledge that it never crosses the even function. So the domain would be from negative infinity to 0, skip over 0 and go out to positive infinity. The range would start at 0 at that horizontal asymptote and be everything above it, but we wouldn't include the horizontal asymptote. And you can see in the table, there's an error where that vertical was trying to approach 0, and it actually says error in the table. All right, getting close. Graph 10, exponential function decreasing. So when it's decreasing, the base is a fraction. So we have 1/2. Or we could move the 2 up, and that could be 2 to the negative x. So there's a couple of ways that could be written. A decreasing function starts high on the left side of the graph and moves to a lower value on the right side of the graph. It can cross the y-axis, and then it has a horizontal asymptote on the x-axis. So it doesn't ever get to that point. It gets really, really close, but it doesn't ever actually reach that. So you can look at the graph here. At -2, it was up at 4. At -1, it was at 2. At 0, it was at 1. And we know that from our base function. Anytime we take a number to the 0 power, that equals 1. That has the characteristic of all exponential functions. And then you can see where at -1, it was up at 2. At 1, it's 1/2, right? And then it kind of goes down from there. So you can see it's approaching 0, but it's not ever going to get there. Graph 11 is exponential increasing, and that technically could be any number to the power of x. So you could have f of x equals 2 to the x, f of x equals 3 to the x, f of x equals 10 to the x. We tend to look at 2 to the x because that's really the smallest base that we can use that allows us to see that behavior of it growing from a low value close to the horizontal asymptote, moving to the right of the graph and moving up and increasing what we say exponentially. So you can see from the table here at -1, it's 1/2, but now at 1, it's 2. And so it goes through the point 0, 1, again, because any number to the 0 power has a function value of 1. And so all parent functions of the form have that 0, 1 point on the graph. Now you can translate them, move them around, and obviously things change. But anytime your base number is a whole number, we're raising it to a positive x value, then we're going to have an increasing function. So the most common ones we look at are 2 to the x, 10 to the x, and e to the x. All right, exponential base e, so that's e to the x. So again, an increasing function. The approximation for e is 2.718281828, and a whole bunch of other stuff. It goes on forever. So that's just one of those numbers. And just like pi, we use the letter e as a symbol that represents that non-terminating, non-repeating decimal. And so base e, again, anything to the 0 power would be 1. So you can see it does have 0, 1 on the graph. E is a number. It's not a fractional base, so that means it's going to increase. So the graph is going to go low on the left side and move up through the point 0, 1 and grow faster and higher on the right side. Again, it has that horizontal asymptote, so there are no values there. And you can see as my x's change, goes to the point 1 and it keeps going on the other side. The next set are logarithmic graphs. So common log means base 10. That's what our numeric system is based on. That's why it's called common log. It's the common number of our numeric system. And we have f of x equals log base 10 of x. But because we know common log is base 10, then you'll see it written log x. And you won't see that subscript 10 very often. So logarithmic functions are reciprocals to exponential functions. And actually, logarithmic functions were written to make exponential functions easier to calculate. They're just a different form of an exponent. And so you can see the graph starts low and grows slowly, and it goes through the point 10, 1. So that's the base. You can see the errors that are occurring there in the table. That's because there is no graph back behind the vertical line. Now, you do have to be careful if you're trying to graph this on a calculator, because it will appear that the logarithm is going to stop once it gets down in here, and it'll just look like it stops. but it really doesn't, because the problem is it's trying to graph numbers that are smaller than a pixel on the calculator, and so it can't actually graph smaller. But you could trace your cursor there and you could keep going when it looks like it's stopped, and you'll see that it's still going to be calculating values for you. It can calculate values smaller than a pixel, it just can't graph them. So anytime we see log, we think common log, and then we look and see if it's base 10. And we can have log base 2, which is binary. We could have log base 16, which is hexadecimal for those computer folks. So there's just different things that you could have. When it's base 10 specifically, it's a common log. There is a calculator function or a key on your calculator that lets you graph common log. And if you look at the reciprocal right above that button, you actually get 10 to the x. So you can see the reciprocal there from the base. And a logarithmic function, natural log, that's log base e. We use log base e a lot in calculus, so you'll get really hopefully comfortable with that this year, and that'll make an easy transition next year. Notice again where exponential functions had horizontal asymptote, logarithmic functions have a vertical asymptote. You cannot take the log of a negative number or 0. So this is one of those what we call uh-oh functions, because the first one would be square root, because you can't take the square root of a negative number and produce a result that's in the real number system. You have another uh-oh function, which would be rational. So if you're trying to divide by 0, that's a big problem, and that's what we call uh-oh. You gotta watch out for those. And logarithms are the other one, because you can't take the square root of a negative number, the logarithm of a negative number, or 0. 0 is where the asymptote is, and there's nothing behind that on the graph. You can see in the table at -1 there's an error, at 0 there's an error. You have the point 1, 0, and then you have some other values. And you can see that this grows a little bit faster than a common log. And so I always tell people, think about the exponential form of that. So e to the x is like a little over 2 as it grows. So when you turn it upside down for the reciprocal, or you invert it, then you're going to get that growth is going to look a bit bigger. When you're in common log, that's the exponential form is 10 to the x. So that 10 is growing really fast. So it gets up there really quick. So when you invert that one, it actually looks like it's growing slower in logarithmic form because of that natural curve. All right, so these are the two we're adding. So I'm not going to spend a lot of time here. I just wanted you to have them all in one place. Common log was the common log and natural log were the last two from Algebra 2. This is called the step function, greatest integers function, floor function. It's called a lot of things. And it has those little double bars around the x, but it kind of looks like a matrix or something like that. And it does this horizontal stepping up, where you can see on one end of the branch the point is included, on the other end it's not. And the reason it's not included is if it were included, if you drew a vertical line there, it wouldn't pass the test. And this is a function, so remember it does have to hold up all the rules for function, and one of them is it has to pass the vertical line test. So when we get into this, we'll talk more about this, but you want to make sure that you know if the little branch, this is the main branch right here that goes from 0 to 1, it's one step out, one step up, one step out, one step up. And we start by including the point at the origin, and when we get to 1, we don't include the point, and then we hop up. So it's kind of like if you're in a parking garage, and if you've done this with your parents, it's like for so many hours, if you're there for 3 hours, you pay $5. If you go any minute over 3 hours, then you have to pay another $1 for the whole hour. So maybe that you did your 3 hours and then you were like 30 minutes into the next hour and had to pay $1, or you could be 45 minutes into the next one and have to pay $1. And so that's what that step is. It's stepping up in prices or something along that line, just to give you an idea. And then the last one doesn't have a fancy name. It's f of x equals absolute value of x over x. What's on top has to be the same as the bottom. And so you could have x over absolute value of x. You could have x plus 1 in absolute value bars, and then x plus 1 on bottom. And so we'll get into that function as you learn a little bit more about that. And it looks like a horizontal line that points to the right, and then a horizontal line that points to the left. And so since we can't divide by 0, remember, this is a fraction, then you can't have anything on the 0, which would be the y-axis. And so then I can just plug in points, right? I can say absolute value of 1 is 1 divided by 1 is 1. Absolute value of 2 is 2 divided by 2 is 1. Absolute value of 3 is 3 divided by 3 is 1. And if I go to the left, absolute value of -1 is 1 divided by -1 makes that a -1. Absolute value of -2 makes that a +2, but you're dividing by -2, so you again get that -1. So you get this characteristic of these two horizontal lines where nothing is on the vertical axis. If that were x plus 1 on top and x plus 1 on bottom, well, the whole graph would shift 1 to the left. So those open circles now would line up on the x value of -1. So we can have transformations that we talk about there. So these are all of the graphs that we are kind of working with and reviewing and using your knowledge. You spent an incredible amount of time in Algebra 2 mastering this function behavior and all of these parent functions. So this is just a resource for you in case you needed a little recap of all of these functions that you studied in pre-cal. I'm sorry, Algebra 2 that we're going to use in pre-cal. All right, hope that helps. Bye.